Alright, this video here is all about the informal idea of a mathematical limit. And I want to start things off by showing you some data here. And this is actual data that came from a Joliet drag strip. So that's where one of those places where you can drive a really fast car, right, as fast as you like. And once you pass the finish line, they give you a little time slip here, which shows you the time that has gone by and what distance you covered, right, in that time. So you can see we have seconds here and then a mixture of feet and miles. So the interesting thing here is once the driver had this time slip, he asked what seemed to be a pretty basic question. And that question was, can we determine at what moment in time I was traveling 60 miles an hour? So I'm going to write that down, 60 miles per hour. And so you'll know that this is a pretty common way of measuring the performance of a vehicle, right? The 0 to 60 miles an hour, and that's what this person was asking about. And so based on the fact that this is in seconds, right, and this is mostly in feet, it's probably a prudent thing to take this and to convert it, right? So we can change 60 miles an hour into 88 feet per second, right? So these are equivalent. So we could reformulate this person's question by saying exactly at what time moment or how long did it take the car, right, to reach 88 feet per second. So that's really the question that we're after. So one of the first things you might think of is when you have a nice set of data like this is to plot the data, right, to generate a graph and to see if you can gain some insight from that. So I'm going to put this graph right up here, right, so we can see it. And what I think I'll do is to also leave the data here so we can look at that as well. Okay, so you can see we have, I believe, 6 data points all together, and you can see them here as well. And so a pretty common thing here is when we have the data plotted, if you notice a trend, right, there are some tools in mathematics and statistics in which you can generate a nice smooth curve, right, something that's really going to describe the trend. And in this case, we're talking about the speed. So we should probably label this as time here, right? So this will be time in seconds. And then up here we have distance, and we're going to measure this in feet because our target here will be that 88 feet per second. So I'm going to just do a rough job here of connecting the dots. We don't have to do a perfect job. Right, so this will just describe the trend, and we'll give this a name because this is some kind of function, right? S of t. So this really describes the position of the Corvette at any moment in time. So we can look at the time moment and then figure out how far the Corvette has traveled. So one of the things that we can do here that is related to the rate is to calculate some average velocities. So you might remember this pretty simple formula from algebra, right? Distance equals rate times time. And this might come to mind because this problem has to do with time and distance, and the question itself is all about the rate, right? How fast that we're traveling. So if we write down rate equals distance over time, right, just by rearranging this, then what we can see is that a question about the speed or the rate of the Corvette is really a division problem, right? Distance divided by time. So you can see here this is the distance traveled, right, divided by the time that has elapsed. So really we have a change in y over a change in x. So this is nothing more than the simple idea of slope, right? So we're just computing this little difference here, and then we have a quotient that's involved there as well. So what I'd like to do is just to show you a few of these calculations, right? So we might start out just by looking at the first 60 feet, right? And this would correspond to just about the first 2 seconds, right? And then we can compute the distance that has been traveled over the time that has elapsed, and this will give us the average speed of the Corvette. Okay, so I'm going to show you this one here, right? This little calculation here. So this is using the 0.734 and the 2.063. So we're using this time information here, and this is corresponding over 60 feet. So this S here corresponds to the curve here that we have that describes the points. So if you do a change in y over a change in x, this is our average speed, 45 feet per second. And you can tell that this falls pretty short of the 88 feet per second that we're looking for. But this would correspond to calculating the slope, right, given the first 2 points. So what I'm going to do is to put the line right in there so you can see it. So I'm going to connect the first 2 points with a little line, and we can see that. Right? So what we're pretty much saying here is that the average velocity, right, is 45 feet per second, but if you think about it geometrically, that corresponds to the steepness of the line, right? So that is really the slope of that line. Okay, so if you want to keep going, what we can do is to look at different data. You might want to now look between 60 and 330 feet, and that would be from about 2 seconds to about 5.5 or so, right? And then you would recalculate. So you'll notice if we now use that data, the formula looks exactly the same, but the result is quite a bit different because the driver is speeding up. So now the average velocity here is 81 feet per second. So if we try to do the same thing here, this corresponds to the second point and the third point, so I will connect those, and then you should be able to see this. Right, so it's something that is visually appealing. So you can see that the red line here is steeper than the green one, right? And then when we go back and think about what this means, you think about the calculations, right? 81 as a slope is steeper than 45. So you can see the analytical calculations compared to the actual steepness of the line. Okay, so something here that's important, a mathematical term, is anytime we have a line that connects 2 points on a graph, there's a special name for that. We call this a secant line. Okay, so there are many secant lines here that you could talk about, but the only problem with this is the idea of a secant line doesn't answer the original person's question, right, about how long does it take to reach 88 feet per second. Because every time we take 2 points on the curve, all we're doing is we're averaging, right? And this person is really asking a question about looking down at the speedometer and saying, when did I actually reach 60 miles an hour? Okay, so to answer this question, it's actually pretty difficult, and it does require very special tools to do it. But the idea behind it is very simple. Okay, so I'm going to generalize a little bit just to build the basic idea, right, the thing that we're going to talk about. And what we're going to say is, suppose we want an actual reading of the car, say, at a given location. And I'll mark this with an arrow just like that. So what you can tell based on what we did is we were always taking 2 points on the curve. So we can do that kind of thing. So we can grab these 2 points and draw a little line, and it's going to give us an average velocity, right? And really a secant line, so you can see it touches the graph at 2 distinct points. But if we take this second point and compare it with the first, and now choose to drag it even closer, then what we're doing is we're shrinking the interval, right? So we're making the window smaller. So if we now keep the first point fixed, but move the second point closer, you'll notice that the slope of the line is going to change, right? And you can see that. So we continue this process, shrinking the interval even more. So now I'm going to connect these last 2 points here that I have in the diagram. And it looks like this. So all of these lines here that you see, these are secant lines. So you can see those secant lines there. But if you really want to get an instantaneous reading, so if you want to know at what moment in time was I traveling exactly at 60 miles an hour, then you really need to take this interval and shrink it to nothing. Okay? So we're going to drag the second point to make it coincide with the first. So that means we will have a single location on the curve, and you will have a line that just touches the curve at 1 point. And so this line is in green. So this line here is called a tangent line. And tangent literally means to touch. And so you can tell with this green line that we're taking 2 points, but really it's a single point on the curve right, where the 2 points coincide, so the green line just touches the curve at 1 point. So if you look at a sequence of secant lines, right, and you let the 2 points coincide, this sequence, right, or these secant lines eventually become a single tangent line. And this tangent line here will correspond to an instantaneous reading. So what we see here on this side is really the average rate of change, right? Because we're looking at 2 points over an interval. Over here we're looking at an instantaneous reading because the 2 points or the interval become nothing, right? Become a single point. And this is the basic idea. This is what we need to answer the man's question, the person who's driving the car. Okay, so I'm going to talk a little bit here about the answer to the question, because this is not so much about getting the answer, it's mostly about talking about the idea of a limit. Okay, so I can tell you, if you do a little bit of heavy lifting here, you can figure out that the answer to the question, right, how long did it take to reach 60 miles an hour, is around 4.2 seconds. So given the information we have, it's actually around 4.17 seconds. Now the way to understand this is if you think about what we just did graphically, you can compare it to what's happening here. So I'll show you in the graphic below, right? So if you take a window, 4.17 to 7, this is a pretty large window of time given that you're speeding down the raceway. And so the average velocity on this window, if you compute that same change in y over change in x, this is about 105 feet per second. And that's over the value that we want. But it corresponds to using 2 values on the curve. But now if you keep the first point fixed and move the second point closer to 4.17, right? So if you look at 4.6 and 4.17, you'll notice our average velocity is now around 90 feet per second. So that's closer to our 88. But you'll notice here that if you look at these numbers in the second column, there is some regularity occurring. So even though these numbers are changing, they appear to be changing at a slower rate. And this is the essence of the idea of a limit, because it appears that the numbers in the rightmost column are approaching a number, and that number would be 88 feet per second. So notice the last interval here, 4.17 to 4.19, is a very small interval of time. And so this is like a snapshot, almost like looking down at your speedometer and saying the reading is 88 feet per second. So we can conclude here that the driver reached that speed probably at some point in this interval. So the collapsing of the intervals here is the same thing we see here in the graphic, right? The 2 points are becoming 1. You almost see 4.17 as a leftmost point and a rightmost point. Okay, so the last idea that I really want to talk about here, just to summarize what this is all about, this is the question that the man driving the car was asking. At what moment in time is my instantaneous rate of change 88 feet per second, right? When was the reading 60 miles an hour? And what we pretty much investigated in this lesson was seemingly a different question, right? And this question was, when is the slope of the tangent line 88 feet per second? So we could see that we're talking about these things here. So this question here is a physical question about how fast the car is going. This is a geometric question, right, about the steepness of a tangent line. And it's no coincidence here that both of these questions, right, have the same answer. And that answer, at least for this problem, is 4.17 seconds. So here what we're really doing is we're interpreting this physically as an instantaneous rate of change, but that corresponds to the steepness of the tangent line. If we talk about average rate of change here, then we're talking about secant lines here. Instantaneous rate of change here, we're talking about tangent lines.